Hello, everyone, and welcome to Tracers from Iowa to Space, unlocking the mysteries of the sun and Earth. We want to allow time for everyone to get logged on and comfortable. So as we continue to welcome our guests, we will get officially started here in a couple more minutes. So sit back, relax, grab your popcorn or whatever snack you have nearby, and we'll get started here in just a couple minutes. If you're just joining us, we'll get ready here to start in just a couple moments. Just letting a few more folks get on. Okay, if you're just joining us, we will get started here very shortly. Okay. Well, welcome everyone. We are so glad you've taken time to join us with us tonight. We are so excited for you to join us tonight for today's webinar, where we will dive into an incredible space mission led right here at the University of Iowa. My name is Leslie Prideaux, and I am the Assistant Vice President of Alumni Engagement at the University of Iowa Center for Advancement, and I'm honored to serve as your moderator this evening. I'll start by getting us all settled in for our time together, then join you in learning throughout the session. And finally, I'll wrap things up as we close out the hour. As most of us are comfortable these days in this virtual setting, please know that all participant videos will be off and microphones will be muted, but we will certainly welcome all of your questions to be submitted through the Q&A feature, as time will be saved at the end to address any of your questions that arise. Okay, Tracers, which stands for Tandem, Reconnection, and Cusp Electrodynamics Reconnaissance Satellites, is a NASA-funded mission designed to explore the powerful interactions between the magnetic fields of the sun and Earth. This groundbreaking research will help answer long-standing questions about space weather, key to understanding how energy, mass, and momentum transfer to near-Earth space. Our University of Iowa team has played a major role in this mission, from developing the initial proposal to building and testing the satellites right here in Iowa before moving on to final preparations in California. So today we are fortunate to have with us the Tracers experts who have been instrumental in making Tracers a reality. Please join me in welcoming Professor Miles, Professor Halekas, Dr. Hospodarsky, and Mr. Dvorsky to share their insights and experiences on this exciting journey. Without further ado, Professor Miles, I turn it over to you. The floor is yours.
Very good. Thank you, Leslie, for the kind introduction. So let me do the traditional Zoom thing. And hopefully at this point, I think you might be seeing a title screen. Perfect. So as was introduced, I'm David Miles. I'm faculty in the Department of Physics and Astronomy at the University of Iowa, and I'm also serving as the principal investigator for Tracers, which is a NASA-funded small explorer satellite mission. So we're taking the build hardware, we're going to take it to space, and we're doing science related to how what the sun does affects us here on Earth. So before we get deep into the mission, let's just talk a little bit about the department. So the Department of Physics and Astronomy has a large cohort and a very proud history of doing research in space exploration. our heritage really comes back to Professor James Van Allen, discoverer of the Earth's radiation belts, and for whom our building is named, the Van Allen Hall. One of the things that we take really seriously is that, we are a teaching institution, we're also a research institution, and we try to mesh those things really to the degree possible. So we have, students at the undergraduate, graduate level, we have research scientists, we have research engineers, and they're all part of this meshed teaching and research exercise. So as an example, we try to involve students really at all levels in our space-based research. Some of you may have heard the term vomit comet, which is a name for this airplane that goes up and does these cool parabolic bounces. And as they're doing these parabolic maneuvers, you create periods of microgravity where essentially the effect of gravity is temporarily negated. So we've done, a bunch of experiments in that environment. And when we do experiments like that, we bring students not just along for the ride, but as key investigators with who are essential to executing these research missions. And we're going to shift over and we're going to tell you about Tracers, which is a large NASA-funded research project. But we carry that same philosophy forward, where we're trying to have our students, not just participating in Tracers, but integral to the whole effort, and where their contribution is really essential to make the project a success. So, University of Iowa Physics and Astronomy, we claim heritage doing things in space back to Explorer 1 in 1958. So this is the famous discovery of the Earth's radiation belts with James Van Allen. Since then, we've had instruments on about 70 spacecraft. And some of those spacecraft you've probably heard of, things like Voyager, Galileo, Juno. There was a mission to the radiation belts called the Radiation Belt Storm Probes, which was then renamed as the Van Allen probes in honor of Dr. James Van Allen. So we like to tie our legacy back to the launch of Explorer 1. The launch of Explorer 1 actually became a whole sequence of missions called the Explorers program at NASA. So I and Rich are actually both at the Explorers program office in NASA Goddard in Maryland at the moment, working Tracers. And so Tracers then is one of these missions, a small Explorers mission. Small in this context is about $165 million. And the trick with an Explorers mission is that the execution of the project is delegated to an institution and to a principal investigator. So NASA has delegated the execution of this project to the University of Iowa. We are carrying it out on their behalf. So I think it's a really exciting project. We're going to tell you a little bit about the science. We're going to tell you a little bit about the instruments that we've put together to do this, the testing flow, where we are in the project, and we'll wrap up by telling you how we're going to get this on orbit. So I want to give credit at this point to the Small Explorers mission was proposed by Professor Craig Kletzing, who was both a friend and a mentor to me. Tragically, Craig passed away quite quickly after the mission had been funded. So there's been a tremendous groundswell at the university of people pulling together, the institution pulling together, really everyone coming together to try to execute Craig's mission. So back in 2016, Craig submitted about a 180-page proposal to do Tracers. And since then, under his leadership, and then, the MASL passed and we've continued to push it forward, we've really been trying to bring to fruition the last project put forward by Professor Kletzing. And with that, I will pass it over to Professor Halekas.
Thanks, David. So I'd like to start just by talking a little bit about the why of the Tracers mission. So first of all, why do we even care about space? Well, as our society becomes more and more dependent on technology, it's also becoming more and more dependent on space. We depend on space for things like communications, for things like GPS, and other things. And as we become more dependent on space, we also become more vulnerable to space, because space is full of all kinds of nasty things, many of them which come out from the sun. So the sun is constantly spewing out particles and energy and electromagnetic radiation. We call this the solar wind, and it flows out from the sun at 1 million miles an hour, sometimes a few million miles an hour when things get exciting. And it washes throughout our solar system and it bombards our Earth and our little magnetic bubble. When it does so, especially when there's a big energetic solar storm, it can damage our infrastructure. It can affect our satellites in space. If it's big enough, it can even affect things like the power grid on the ground or transatlantic cables and things like that. Now, we can mitigate those effects if we can learn how to predict this space weather, as we call it. But we need to really understand the processes that lead to space weather. And to do that, we have to understand this whole system and learn how to predict it. And then we can keep our technological infrastructure safe. Now, if you go to the next slide, you might ask, well, don't we have this big magnetic shield that protects us from all of this stuff? And the answer is yes, we do have a big magnetic shield, and it does protect us from a lot of this stuff. But this magnetic shield is unfortunately permeable. It has big cracks that can form in it to let solar energy and matter through. And this occurs by a process called magnetic reconnection. When the sun's magnetic field and the Earth's magnetic field are aligned just right, or actually anti-aligned, they can merge and basically rip a big hole in the Earth's magnetic field and let solar particles and energy come streaming down those magnetic field lines. They tend to go down the field lines into this kind of funnel-shaped region that you see over the poles of the Earth. We call that funnel the cusp. We're very creative with names that way. And that cusp is where Tracers is going to be doing its prime science. Now, we know some things about this process. We know that it's not perfectly steady. It doesn't happen at a constant rate. It doesn't happen at the same place at the same time all the time. But we don't know exactly how it varies. So if you go to the next slide and then click forward one more, there's a couple things that could happen. One is that it could vary with time. It could kind of blink on and off like a strobe light, say. The other is that it could vary with space. It could move back and forth across our magnetic shield like a floodlight, if you will. Or if you go to the next slide, maybe it's some mix of all of the above. Maybe it's like a fireworks show where this is varying both with space and time and popping off all over the place. I personally like the fireworks model myself. But how do we answer this question, and how do we differentiate between these possibilities that we don't know which actually operates? Well, to do it, we need not just one measurement point, but two. With a single spacecraft or a single measurement point, when you see things varying, you never know whether they're varying with space as you move along the orbit or whether they're varying with time. And so to tear that apart, we have to have actually two measurement points. So if you go to the next slide, this is not actually the first time that we've done this. We had a precursor mission of sorts, which we called TRACE. This mission was also led by Professor Kletzing. And in this mission, we launched 2 rockets into this cusp region that I described with a very similar instrument complement to what we're going to have on Tracers. So this precursor mission kind of proved to us that the instruments that we're going to have will work together and that they'll allow us to solve the problem that we're trying to solve. But this was just one shot. You got one measurement in the cusp, and then the mission was over 10 minutes later. If you go to the next slide, what we're going to do with Tracers is we're going to do this thousands of times. So this again is Professor Kletzing presenting his mission concept. And the idea is that we're going to have 2 spacecraft in orbit rather than just rockets going up and coming down. Those 2 spacecraft are going to orbit around the Earth at low altitude, but they're going to go through this very special cusp region where everything is connected out to the front of the Earth's magnetic bubble. And when reconnection happens out there, all of the particles and electromagnetic energy will come streaming down the cusp towards us, and we will measure it with these 2 tracer spacecraft following each other in quick succession through the cusp. And with those 2 closely spaced measurement points, we hope to be able to tell whether it's a spotlight or a strobe light or a fireworks show or something that we haven't even imagined yet. If you go to the next slide, I'll just talk a little bit about how many people it takes to put together a mission like this. So we've been working on this mission for many years now, and you see there in the image actually just a small part of the team. That's actually just the science team at a recent science team meeting. Behind that science team, there's a whole team of engineers and technical staff. There are administrative staff that have been helping us out, financial people. It takes a huge army of people to do all of this. And I really want to credit all the people that have contributed to tracers along the way, some of whom I see listening to this webinar, which is really cool. I recognize a lot of names on the attendance list. So just to highlight some of the pieces that have to come together for this to work, we have a spacecraft, which is built by a company called Millennium Spacecraft Systems in El Segundo. We have a bunch of scientific instruments making different measurements. We have an ion instrument coming from Southwest Research Institute in San Antonio. We have an electric field instrument coming from UC Berkeley. We have a magnetometer coming from UCLA. And then we have 3 instruments coming from Iowa, as well as a main electronics box, which is kind of the brain of the whole operation. And you'll hear more about those in just a second. Now, as if that isn't all good enough, along with this, we have a ride-along project, which is called Ochre. This is another sounding rocket, which we're going to put together and we're going to launch during the Tracer's mission. So we'll actually get 3 points instead of 2. And the cool thing about this rocket is it's being put together not by a bunch of professional scientists, but it's being put together by students. So these students are building essentially cheap copies of the Tracer's instruments, but they're learning how to put these instruments together, and they're learning how to be the next generation of scientists that will carry on and propose the next missions to solve the problems that we haven't even thought of yet. So at this point, I'd like to hand it off to George Hospodarsky, who's a research scientist here in the department, and he's going to tell you a bit more about the instruments, what they do, how we put them together, et cetera.
Thank you. Can you go to the next slide, please? Thanks. As Professor Halekas said, we're measuring the particles and fields in the Earth's cups, and that's how we do the science and answer the science questions. And we have 3 instruments. There are actually 2 identical spacecraft, 6 instruments on each spacecraft, and 3 of those 6, so a total of 6 University of Iowa instruments, 12 instruments total because they're identical on each spacecraft. And I'm going to talk about the University of Iowa instruments, and we'll go to the next slide. The first one I'm going to talk about is the analyzer for Cusp electrons, or ACE, and Professor Halekas is the PI for this, so if I say anything wrong, he should correct me. It's a top hat electrostatic analyzer. It's designed to measure electrons from about 20 eV to 15 keV. And the way it works, if you look at that schematic that has the orange sort of drawing on it in the middle of the image, electrons stream in through the opening, and a high voltage is applied to the 2 hemispheric spheres there. And that affects the trajectory of the electrons depending on what voltage is applied. So if the right voltage is applied for the right energetic energy of the electrons, they stream in through that gap and hit the microchannel plate detectors. And basically this instrument can determine what energy the electrons are, how many there are, and what direction they're coming from, and to resolve basically the electron part of the particles in the Cusp region. If we go to the next slide, the magnetic search coil, and this is the one I helped build or in charge of, it measures AC magnetic fields from about 1 hertz to 1 kilohertz. The way a search coil works is basically thousands of turns of wire wrapped on a high permeability magnetic rod. In the case of tracers, it's 26,000 turns of wire times 2 for each axis. The magnitude of the magnetic field and the frequency of the magnetic field determines what voltage and current comes out of that coil. And by measuring that with the electric preamp and then sending the signal to the spacecraft to be digitized, we can determine what magnetic waves and how much magnetic energy at the higher frequencies we're encountering with the spacecraft. The magnetic search coil and the magnetometers are mounted on booms to get away from the spacecraft because these sensors are very sensitive. And if there's any interference due to the other instruments or the spacecraft, they will actually pick that up. And so almost on every NASA mission, we try to get the search coils and the magnetometers away from the spacecraft. And then for tracers, it's about 0.7 meters. And to give you an idea of the size of the search coil, I'm holding that's actually the Viper one we built for a sounding rocket, but mechanically it's almost identical to the tracers ones, which are shown in the bottom pictures. We can go to the next slide. And the other instrument built at Iowa is called MAGIC. It's an MPR 7128.8 tech demo, and that has to do with which project program in NASA funded it. This is a technology development project. It was actually added to tracers after the main tracers part was selected. And it has two main parts. One is to help develop low noise fluxgate cores. The cores are one of the primary parts of fluxgate magnetometers. There's a long story behind that. They were actually, the majority of the ones used by NASA were built in the 1960s by a company that no longer exists. And the formula for those actually have been lost with time. And so Professor Miles had been working at remanufacturing cores with the same sensitivity as these heritage cores. The other part of this was Dr. Miles has come up with a method. The majority of past ring cores are circular, like the bottom left corner. He's come up with a design which uses a racetrack core and to be put into a sensor, which he calls the Tesseract sensor. So part of the MAGIC technology demonstration is they're flying on one spacecraft, what I'll call a typical ring core sensor design, and then the other he's flying the Tesseract sensor. And the idea is to see how these operate in space and compare them, the designs, because the Tesseract should be more mechanically stable and temperature stable. These are also mounted on a boom. MAGIC is shown where the arrow is, while the outer one is the magnetometer from UCLA. And again, the reason is to get away from the spacecraft, but it's really nice to have two magnetometers on the same boom, because if there is interference caused by the spacecraft, you can actually subtract that out by having two measurements at different distances from the spacecraft. We'll go to the next slide. The last thing we have from Iowa is the main electronics box. And this contains the electronics from the EFI instrument, the magnetometer instrument, and the computer data processing unit, the CDPU, that was built by New Hampshire, which collects all the data from the instruments, packages them up, and sends them to the spacecraft to be sent down the ground. The other thing the MEB contains, you see a little purple thing, that's a guitar pick. Professor Kletzing was a musician and belonged to a number of different bands, and he loved his music. And so in honor of him, we've applied one of his guitar picks to both of the MEB boxes, and they will fly in space in honor of Professor Kletzing. We can go to the next slide. We have a number of test facilities at Iowa to test these instruments, because before we want to make sure they work and can survive the environment of space and launch, because once something launches, you can't fix it anymore. And so if it's going to break, we want to break it before it launches. So we have a number of vacuum chambers in the department. This is one of them, and Professor Halekas is performing a test on the ACE instrument, I believe, in this picture. The particle instruments have to be tested in vacuum to do the high voltage part of the test, because the voltages are so high that if you test them in the atmosphere, they can very easily arc due to contamination. And so you have to test these in vacuum. The next slide, I believe, shows the EMI chamber we have at Iowa. This is an electromagnetic shield chamber. We're taking a picture through the door here. When the doors close, that basically shields the instruments that we're trying to test from radio stations or any other electromagnetic environment that can mess up our measurements. And this is basically, we test everything we send in space to make sure they're not transmitting signals that might interfere with each other. The next slide shows the vibration test facility, because one of the biggest things we have to worry about is when you launch something on a rocket, it quite often gets shooken a great deal. And we got to make sure, nothing breaks or falls apart during launch. And so every instrument, and then later on the spacecraft with the instruments on it, undergo a vibration test. And this is a picture of actually the MAGIC sensor being tested. And this is Rich Dvorsky checking something out. We go to the next slide. This is just a picture of a couple of engineers, Christian Hansen and Kate Morris, we're in the control room of the vibration facility, going through the test procedure. The next slide. And we also have a thermal vacuum chamber in the department. I mentioned earlier we have vacuum chamber. What's different about this one, besides it's larger, is that it actually has thermal control in it too. Liquid nitrogen can be pumped into it to cool things down, and also there are a number of heaters. And so with this chamber, we actually simulate the temperatures the instruments expect to see in space. And we run through a series of cycles before when we're testing the instruments, again, to make sure everything works the way we expect it to. You can go to the next slide. When the other teams like at UCLA and Berkeley finished their instruments, they shipped them to Iowa to integrate with the rest of the instruments and put their electronics in the main electronics box. And this is a picture on the left of the test from the first suite, along with some of the team members from Berkeley and UCLA and University of New Hampshire. After we tested the instruments on the bench to make sure everything was working properly, we went to the clean room and we started installing them on a 3D flat sat assembly, and that's what is shown in the middle. And if we go to the next slide, that actually shows it even better. This is a life-size model of the spacecraft. It allowed us to mount the instruments where they belong, work on how the cable should be routed between the different instruments. But in this picture, you can see the 4 EFI antenna spacers. That's the black and red items, sort of the middle of the thing. The main electronics box. ACE is on the left. You can see the backside of ACE on the side panel, and then ACI is on the right there. And this allows us to run tests with everything in sort of the same configuration they would be on the spacecraft. You can go to the next slide. And this is just we have a control lab and where we test the instruments when they're in the clean room on the flat sat. This is the control room outside, so people don't have to be dressed up in the bunny suits that were shown in the other picture. You can go to the next slide. And then after we did all this testing in Iowa in July, we shipped the instruments and the ground support equipment to the spacecraft provider in LA. We used FedEx, the custom shipping. Basically, 2 truck drivers drove it straight from Iowa to the Millennium Aerospace, and they're just packing up the truck. And I'm going to pass it off to Rich, where he can talk about testing done with the spacecraft.
Next slide. All right. So as George mentioned, the key thing on a mission like this, particularly the part of the mission that goes to space, we do a lot of testing on it before we ever put it on the rocket and send it to space. So as part of that, after we even ship the items from Iowa to California to be integrated on the satellite, the first thing we do is basically put our entire test setup, reassemble it in California, and rerun a lot of our tests. So what you can see here on the photo on the left, this is after we showed up in El Segundo at Millennium Space Systems. We reassembled all of our instruments onto our fixture where we reperformed our test, or what we call our CPT, or Comprehensive Performance Test. What the CPT does is gives us a baseline for how the instruments are performing and meeting their performance requirements. So a lot of the things that we do, a lot of the tests that we do are checks to make sure that the instrument is meeting its designed requirements, so that when we get to space, we know that we'll be able to get the science return out of the mission, or at least collect the data that we are interested in. So if you look to the right of that is after we started integrating those instruments from our test fixture into the spacecraft. So as you can see, now that we have installed the instruments in the spacecraft, we have a lot of room to work around on the left. And then once we move over to the spacecraft or satellite, you can see that we have things like propulsion tanks, thrusters. We have separate decks now on the top and bottom that are all part of the tracer stack. If you move to the next slide, you can see, so this image actually doesn't quite show the test itself, but this is actually just after we finished the test. So as George mentioned, we did testing at the instrument level for the electromagnetic interference and compatibility testing. What we do is we test really high fidelity at the component or instrument level for things like magnetic interference, how susceptible the instrument is to electromagnetic interference. We want to make sure that on orbit, if it was how much it would radiate. So a lot of the instruments that we have on the tracer's mission are actually really good at detecting electromagnetic interference. So we want the vehicle, we want all the other instruments to be as quiet as possible so that we don't interfere with the measurements of the instruments. We repeat this test again at the satellite level with the whole system put together. Part of this is to make sure that all of the instruments and the satellite components are all compatible with each other so that we aren't getting that interference. But then also we're checking to make sure that the emissions that this system have do not exceed any of the limits that we are allowed when we are working with the launch vehicle. We are also looking to make sure that any of the emissions that may be present at the range or during the testing at the range, the launch range, will not have a degrading effect to our satellite. So we'll move on to the next test. So before I move on to the next test, I want to at least describe kind of how the operations of a tracer's satellite works. So there's two satellites. One unique thing, or I wouldn't say overly unique, but we are what you consider a spinning satellite. So the tracer's satellites spin about that central axis of the body. So kind of keeping those four stator booms in plane is how the tracer satellites will spin on orbit. So for this, we want to make sure that the vehicle itself is well balanced before we launch it. So we want to make sure that that spin axis is going through the geometric center of the satellite, and we want to make sure that it's well balanced so we don't get any wobbles. If you go to the next slide, what you'll see, and this is not a great picture of it, but below the bottom of the tracer satellite is a giant machine that is somewhat similar to how you, like a balancer for a car tire. And so what we did is we did a balancing of each satellite independently to make sure that the spin axis is through the center of the vehicle. We are also making sure that the center of gravity, so the position of the center of gravity of each satellite is basically through that same center line. That's very important for us because the way that our vehicles are dispensed off of the rocket, essentially there's a spring-loaded interface that when we dispense the vehicle, it releases it and springs it directly straight out away from that plane. So we want to make sure that we have a high accuracy mass number, we have a high accuracy center of gravity, and that we are measuring the product of inertia to make sure that it is as close to zero as possible, or about the center line of the tracer satellite. So what you can see here is just how we mounted to that balancer. And then we had little plates that are installed kind of at the top and bottom of the plane, the mounting plane, and then if you go a little bit higher, there's another plane. These little weights were used to balance the satellite to get that perfect center of gravity position, and then that near zero product of inertia. Next slide. So the next test that we performed was the vibration test. So the vibration test is similar to what we had at the University of Iowa, where we were testing each component. Now that we have integrated all of the instruments onto the satellite, we repeat a similar vibration test plan that we did at the instrument level, but with different interface loads. And these are interface loads that were defined with the launch vehicle provider. And so as we performed the test, we basically tested on all three axes, just like we did on the component level tests. And you can see in this picture, this is both of the tracer satellites stacked in their kind of launch configuration. And then below, the vibration shaker is almost like a giant subwoofer that's moving up and down to give us that vibration excitation, similar to what we would see on launch. Next slide. This is just another picture showing actually with the vehicle on its side. So we are on the slip plate of the vibration table. This is to excite provide an excitation in the lateral directions of this. And then this is the team that was out helping perform the vibration test on the Tracer's satellite stack. Next slide. So the next test, similar to what George talked about with the thermal vacuum chamber at the University of Iowa, we repeat the full level or the full thermal vacuum tests at the satellite level. In this picture, you'll see that we have both tracer satellites stacked next to each other on the end of a giant plate that makes up the end of the chamber. And then what you'll see around the satellite are heaters that will apply appropriate heat loads. And as George mentioned, we close up the chamber, we pump all the air out of it, and then we apply heat loads to simulate the thermal environment that we would see in space, and then also the deep vacuum that we would see in space, so that we are testing the satellite over its predicted environment thermally. Go to the next slide. And this is just showing that same test fixture. And then you can see kind of from the top, those little lines that look like grids, those are heaters, or what we call cow rod heaters, that are applying heat to the top and bottom of the satellite. The one thing I'll note, so the image you see here is the specialized paint on the bottom of each vehicle, which is what we consider a radiator. This is how we dissipate some of that, the heat that is produced as the instruments are operating and the satellite is operating. And this is a big part of how we make sure that we can keep all the instruments in an appropriate operating temperature range while they're on orbit. Next slide. So this final photo is actually us after we completed the thermal vacuum testing, and we were removing the satellites from that test fixture. And then they have moved into a separate area where we performed additional testing to make sure that the satellites both survived all of the tests without any degradation of performance or damage. And then the next step is prepping them to head to the launch site. And from here, I'll hand it off to Dr. Miles.
Perfect. Thank you, Rich. So the picture you're seeing here is the state of the mission as of about a week ago. So we went through this really exhaustive environmental test campaign. We knew going into it that all of the instruments worked. We did this really rigorous series of tests. We did, a verification after those tests that all of the instruments still worked. At this point, we basically put the spacecraft down, and we're just getting ready to put them in the shipping container so we can send them off to the launch pad. So I'm going to tell you just briefly what is going to happen next. So our ride to space is what's called a cake topper. And we're riding on a Falcon 9, which is a large SpaceX rocket. So what we're going to do is take our stack of spacecraft here, we destack them, we put them in shipping containers, we load all that in the back of a truck. We're going to drive it from Los Angeles down to Vandenberg Space Force Base. We're going to unpack them, we're going to put them back together, we're going to check that they still work. Then that stack of spacecraft gets put on top of this big pillar here in the middle. This is an example of what's called a ride share. So if you go back in the day, NASA would buy a dedicated launch for each spacecraft. That's really convenient, lovely if you can get it, but in a world of constrained resources, the more efficient thing to do is that we're the cake topper, we sit up top, we negotiate with SpaceX, where does this rocket going to go, where is it going to tip us off, and then SpaceX goes and finds other people that want to go to a similar orbit, and it sells the space down here. So essentially, like, we're a big bus, and we're going to drive the bus, and other people get off on the way. So once we're at Vandenberg, we go on top of this pedestal. There's these other ride shares down underneath us, and then we get mounted on top of a Falcon 9. For people that don't know, Vandenberg Space Force Base is down here on the coast. So lovely place. You're at the coast, so you can launch over the water, which is, the safe thing to do. And so once we're down at the base, we're going to put everything together, we're going to test, and then we will be right up here on top of the Falcon 9. We're going to take a ride up to about 590-kilometer altitude. The nose cone's going to open up. They dispense one spacecraft. They dispense the other spacecraft. We spend a few days basically getting control of the spacecraft, getting everything checked out, and then we're going to start doing science. One of the great things about having SpaceX as a launch provider is they're going to drop the satellites exactly where they need to be to do science. So basically, as soon as we're on orbit and we have our spacecraft checked out, we turn all the instruments on, and we're in position to start collecting the data that we need to do our science. So really, what comes next at that point? So there's a launch date. We're going to call that L. We have about 2 weeks we've given ourselves to check the spacecraft out, and we're going to start releasing data internal to the mission. At about a month after launch, we're going to start releasing some of the higher level, more sophisticated data products. And then really quickly after that, we subscribe to the NASA concept, which I think is actually a great idea, of open data products. So there's a point where basically launch plus 4 months that all of our data gets made available on the internet under an open use policy. And other people in the scientific community here in the US, other places in the world, can come get that data and start doing their own science. So basically, very quickly after launch, Tracers is committed to making this data available so that we have science that we want to do, but everyone else in the scientific community is free to come get this data and start doing good and productive things with it. At about 12 months after this end of the checkout period, that's the end of our primary mission. And at that point, we should have done the things that we promised to do. We should have closed our basic science requirements. And at that point, we'll start, talking with NASA about what other cool things you can do with these satellites. All right. So we've told you a lot about Tracers, the spacecraft. I do want to plug a really cool thing that's coming. So one of the advantages of being at a university is we've got a lot of really talented students. So we brought a student in and we challenged them. Lego makes some really cool tools. If you know what a Tracers is, could you go make us Lego Tracers? And the answer is yes. So there's actually a complete Lego model that's been designed, and it's shortly going to get posted up on a website. So if you're interested, you can go buy yourself a Tracers Lego model. You'll get all the pieces, you'll get all the instructions. You can put together one Tracers, you can put together two Tracers, you can smush them together, and you actually get the Tracers flight stack. At significantly smaller scale. This is what we're going to launch. We're going to go do science. So I think this is a great example of, a fun outreach activity related to Tracers, and I think a really cool project for a student. All right. Tracers is great. We're all really excited to see it coming. We're excited to see it on launch. We're excited to do the science behind it. Iowa is committed not just to Tracers, but to, a long-term endeavor in space-based research. So there's lots of other really neat things coming. One thing that I want to plug is that one of the enabling technologies that has really emerged in the last 5 to 10 years is the ability to do things small. So a spacecraft that used to be the size of a bus is now maybe the size of a washing machine, but to the modernization and some of our new technology developments, you can also do that on a spacecraft the size of a couple loaves of bread. And we as a university are really well positioned. We have instruments that we can make at reasonable cost at very small size. So we can do, the next Tracers may not be the size of a washing machine. It might be something like this, the size of 4 loaves of bread. And that's something that we can do, the instruments and all of the integration, all the tests, at the University of Iowa very quickly and at reasonable scale. So we're excited looking forward to all of the other interesting missions that are coming, and we're excited by the emergence of the ability to do missions like Tracers, but at smaller scale with miniature instruments and at really reasonable cost. And I think that's an area that Iowa is really positioned to excel at. So Tracers is going to launch in 2025. It is going to address this really long-standing question in magnetospheric physics. This is the question of, as the sun sort of blows the solar wind at the Earth, it arrives at the magnetic field, this bubble, the shield that Professor Halekas talked about, and sometimes these systems interact, so that interaction can move around, it can turn on, it can turn off. Tracers, because it has 2 spacecraft, is uniquely positioned to sample that interaction and sample it again. And instead of doing that at like 90 or 120-minute separation or multiple day separations, we can take two measurements very quickly, 10 seconds apart, 30 seconds apart, a minute apart, and we can pick apart the time scales under which this interaction happens. To solve that problem, we've built two spacecraft with a really robust plasma instrument suite. So if you go to near Earth space, low Earth orbit, and you want to study that environment, it is a plasma. To measure that, you need the electric field, the magnetic field, you use the particles. We measure all of those things. So this is a powerful measurement platform, not only to go do the tracer science, but also it's a platform that can be repositioned to do other kinds of science. We can go study the northern lights. We can understand, how does the physics work that accelerate the electrons that beat on the top of the atmosphere and create the northern lights. We have a huge amount of fuel in these spacecraft, so we're fueled up for a long mission and hopefully for many, many years of great science. So that's the end of the package that we have together for you. I think at this point, there's an opportunity to take questions. Before we do that, I did want to say thank you to everyone to taking the time to be involved. And we look forward to chatting.
Great. Thank you all so much. I know that everybody on this webinar, if I could get my camera to work. There we go. I know everyone on this webinar just probably is sitting here with their minds blown like I am. This is just incredible that this work is happening at the University of Iowa, and it makes me so proud to even be remotely connected to you all. So thank you so much for sharing your insights and this wonderful information. We have some fantastic questions, and I'm very excited to throw this first one at you. When Professor Hawk from the University of Northern Iowa has this question for you. When I took beginning astronomy in fall 1971 with Professor Van Allen, he brought into lecture a device he said would be on Voyager. Neither he nor anyone in the class was in a sterile suit. Was that less of an issue then, perhaps less sensitive instrument, or would that device be decontaminated before the launch?
So I will say I was not around back then, and I know that the approaches have changed a little bit. But contamination, it really depends on what you're trying to measure. So if you are my instrument and you're measuring the magnetic field, I am incredibly sensitive to a tiny bit of iron scrap ending up on the lid of the instrument. That will contaminate my instrument terribly. But you could drop the sensor in a bucket of muddy water and it won't affect my function at all. If you talk to Professor Halekas, he has a very different set of concerns when it comes to contamination. So when we put together a mission like this, you build a list of all of the things that the different subsystems are sensitive to, and then you build and execute the project in a way that you make sure you're sensitive to all of those things. And sometimes that means the dirty things get cleaned, and sometimes that means that materials that can't fly don't fly. But we come up with different processes depending on what different instruments are sensitive to.
The questions are rolling in. In an increasingly uncertain federal funding environment, what do people, especially people in Congress and the executive branch who don't study or follow solar, weather, or wind, need to know about your crucial work so they can understand how important this research is to their everyday lives and the technology and tools they depend upon?
So from my point of view, we live on a planet, and that planet exists in space. And space is increasingly key to what we do. We deliver services from space. The reason that your phone can navigate is based on the satellites that are in space. We depend on space to do our lives. And so it behooves us to understand that, partially because it's interesting, partially because it helps us to control risk. And so, in a world that is increasingly technology dependent, we want to understand the environment that we're in, because we do more and more things from space. I also think that when we make that argument, sometimes we overlook the fact that we have and will continue to be a leader in space exploration. No, we do this because there's great science to be done. We do it because it's hard, and we do it because it's interesting. And I think that all of those things are still true.
Excellent. So I think people were excited about your Legos. Is the website for the Lego Tracers model rebrickable, and will there be a notification sent out when it's available?
It is not currently orderable, but we will circulate that link as soon as it is, because I too am very excited about the Tracers Lego model.
I'm definitely going to need a few of those. What is the distance between the two crafts once they're in orbit?
That sounds like a really good question for my chief engineer.
Yeah. So I'll give you the time. So tracers will be between 10 seconds and 120 seconds separation. So when we dispense within 2 orbits, we'll be a little over 1 kilometer, but then that opens up kind of to that a bigger distance than that. I don't have the distance in kilometers off the top of my head, but the separation is in time by, said 10 to 120 seconds nominally.
Yeah. So as Rich has said to me, if at any point the Tracers spacecraft are actually flying like this, terribly bad things have happened.
Yeah, no, that's way too close.
I know you had the slide on the Launch Plus dates, but we have a few folks asking about the actual launch date.
So deciding on a final launch date is a complicated thing, particularly on a ride share where there's a bunch of stakeholders involved. So we're going to launch in this summer, but we're not prepared to commit to a date yet. So we're still working that with our partners at NASA and at SpaceX.
That makes sense. A question about what are all of the black boxes all over the side of the spacecraft?
The small little black boxes that you're likely seeing are the solar cells. So if you look at the image, I don't know if there's any more images that we can go back to on the slide deck.
Let me see.
Yeah, so all the little black boxes that you see, those are all solar cells. So if you look, Tracers is basically every side of it except for one side is covered in solar arrays. So that's what we use to be able to charge our batteries and be able to perform the mission, to have enough power to perform the mission, operate all the instruments, heat the instruments, operate all of the guidance, navigation, control, all the electronics that are used on the satellite.
Yeah, so we launch with a large but finite amount of fuel. Great. So we want to use that fuel as sparingly as possible, because when it's gone, we don't get any more. So we're going to use that fuel to move the spacecraft around, to lift it up or to change its orbit. But everything else we try to do with electricity. So we're solar powered, we're covered in solar panels, because that's where we get our energy from.
Makes sense. A question about if we will be able to see these satellites orbiting from the ground in Iowa.
So I think it's possible, and there are online tools for this. You need kind of a Goldilocks condition of where you are, where the satellite is, and where the sun is. And there are online tools that sometimes help you do this. So I think it's possible, but you need a tool to help you, and you need a pretty special circumstance.
Makes sense. A question regarding any issues that were identified during any of the tests after shipping it to California, and if so, what was the process to repair when it was no longer here in Iowa?
As far as issues, I don't think there was any major issues with the instruments that were built by Iowa. Obviously as you're integrating a bunch of instruments to a satellite, things come up. And so there's nothing that's jumping off the top of my head. There's a typical process. So before we do any repairs on any of the instruments, particularly after they've gone through their pre-shipment review, we follow a pretty defined process before we make any repairs. So there's a lot of approvals that happen. And we work with our quality assurance and safety and mission assurance team. But yeah, there wasn't anything notable with the instruments that we had to do between shipment and integration into the satellite.
Yeah, and we work really hard in a programming way so that, stuff gets tested at the component level, and then you roll those components into assemblies, and the assemblies become larger assemblies, and bigger assemblies become spacecraft, so that if there's going to be a failure or there's going to be a problem, you diagnose it as early as possible. Because if you find that there's an issue with an instrument, which there have been issues with instruments, but because of that process, we found those problems when the instruments were at Iowa. And then we could tear them apart, we could affect the repair. That's a hard and labor-intensive process, but it would be 1,000 times worse if we also had to tear the whole spacecraft apart to go get that instrument before we affected that repair. So I think through having a good plan and some very careful execution, so far we've caught problems at times when they were relatively straightforward to fix. And that's really what the mission planning and this development flow is designed to accomplish.
Excellent. What energy source is used to propel the satellites into their positions in space?
So we have kind of one nice advantage with our current launch vehicle. So they're going to drop us at our ideal altitude. We do have a couple of different ways that we make changes to maintain the orbit, and we have a propulsion system that uses hydrazine, a hydrazine monopropellant. The other thing that we use, that we do most of our maneuvers with, are magnetic torque coils. So we use that, as David said, we use the power that is generated from our solar cells to drive a coil of wire to be able to make attitude adjustments with our vehicle, and we can change the spin rate using our torque coils. So we have a couple of different options, but the hydrazine is mostly used just for orbit maintenance.
Excellent. Question about if the team is planning to be on the West Coast to watch the launch in person.
Absolutely. I wouldn't miss it for the world.
That's what I was hoping to hear.
So actually, I'm hoping that Zach is going to tell us all of the secret places to watch the launch, because I happen to know Zach Lupin. He's a former student from Iowa, and I'm pretty sure he knows all the super secret places up in the hill above Vandenberg where you can get a really good view of the launch. So Zach, send me an email or something and let me know where that is.
I love the connections. Let's see. The term tesseract has a meaning for me as a mathematician, and of course, it also appears in Madeleine L'Engle's book, A Wrinkle in Time. Did you choose the term for this mission, or has it been in use for a while?
So when we were building the tesseract, let me back up to it. We were trying to build a sensor that had very high symmetry, because if you look at the sensor in the middle, it's asymmetric. So as it heats and cools, it flexes. So we were trying to get all of the physics we needed with the cores and the coils of wire, but build it in a way that was highly symmetric. And that's how we ended up with the thing on the right. And then when I looked at that, I said, that looks like the mathematical concept of a tesseract, a 4-dimensional sphere unpacked into 3 dimensions. And at that point, the name had sort of stuck. At that point, people also noticed that the name Tesseract looks like a thing from a bunch of very popular Marvel movies. So depending on, how you choose to retcon it, this is either, at a 4-dimensional cube unpacked into 3 dimensions, or it's the cool shiny thing from the Marvel Avengers movies.
I love it. This is probably our last question. What is the data transmission rate from the orbiters?
Yeah, about say 6 megabit per second when we have a ground contact. So each ground contact is about 8 minutes per contact. In nominal science mission, will be we'll have 1 contact per vehicle per day.
Excellent. Well, a huge thank you to everyone who attended tonight and for the excellent questions. I think the conversation after the presentation has been almost just as informative. So thank you so much again. Thank you all for sharing your knowledge and giving us a behind the scenes look at this amazing mission. And thank you all for joining us. You will receive a follow-up email with additional information, so please keep an eye out for that. And finally, you can always check out more ways to get involved, attend events, and more opportunities at foriowa.org. So with that, we are officially going to close with a final thank you. Have a great evening, everyone.
Thanks all.
Thank you, everyone.